Section 8.2, angular velocity and angular acceleration. So as we think about our angular displacement, the delta theta that we have here, we know that the angular position or the angular displacement can be different, right? It can be changing at different rates. So how do we describe the rate at which that angular displacement is changing? Is it moving really slowly, or is it rotating faster? Well, if we want to talk about that rate of displacement change, that's going to be nothing other than our velocity. So our definition of average angular velocity is the angular displacement divided by the elapsed time, which we could write in symbols where our angular velocity is going to be this curvy w. The curvy w is known as omega, a lowercase omega. That's another Greek letter, and that's just because we are out of English letters. There just aren't enough. So we start using Greek ones, especially with angular variables. So that is the omega, the curvy w. So you want to make sure to always draw it extra curvy as opposed to straight lines. We don't want straight lines here. W is going to always be our work or our weight or watts, for instance. So curvy w for omega, and that's equal to the angular displacement, delta theta, divided by the time elapsed, delta t. Our SI unit of angular velocity will be our SI units of the angular displacement divided by time. So radians per second, which is abbreviated as rad divided by s. So there we have it. This is following the same format as our standard linear velocity of displacement over time. We just now have some funnier variables to work with. Let's check an example of this, a gymnast on a high bar. A gymnast on a high bar swings through 2 revolutions in a time of 1.9 seconds as shown in the figure. Find the average angular velocity of the gymnast. Right, so we know we want to find that omega, and the bar over it means that it's an average, because it might be that the gymnast is moving faster at some point, slower at others. We can find the average angular velocity, and that can help us out in a number of situations alone. You'll notice it says as shown in the figure. So as we look at the figure, the 2 revolutions are going in which direction? Notice that they are going in a clockwise direction, which is abbreviated as CW. Remember, clockwise direction, what does that tell us about the angular displacement? It's going to be the negative direction. So that's an important note to take here, something that can be easy to miss, but that will follow the same convention as the book, and so it's helpful to be able to match the book in that, as well as many other textbooks use this same approach. All right, so we know that there's these 2 revolutions in the negative direction and the time of 1.9 seconds. Now, 2 revolutions, what is that? 2 revolutions, that's 2 trips around, but it's not yet in terms of our SI units for angular displacement, right? Angular displacement needs to be in radians. So how do we go from a revolution to a radian? Well, we can remember if there's 1 revolution, when we have 1 revolution, that corresponds to 1 complete rotation around, which we saw was 2 pi radians. So by remembering that, we can then say, okay, if this is 2 revolutions, then that's going to be 2 times 2 pi, or 4 pi radians. 2 revolutions is equal to twice as many radians, 4 pi radians. All right, so with these factors, noting as well, like I said, that it will be a negative because of that clockwise direction, we can do our analysis. So let's take a look. Our angular displacement is negative 2 revolutions because of that direction being clockwise, times 2 pi radians per rev. That ends up being 4 pi radians, which is, if you multiply it out, negative 12.6 radians. typically the pi's will be multiplied out and we'll just have answers in decimal format. If you then want to find your average velocity, we know that average velocity is the angular displacement divided by the time. So we have the angular displacement, negative 12.6 radians, divided by 1.9 seconds. And that comes out to negative 6.63 radians per second. Notice the angular velocity here is negative as well. That tells you that the gymnast is rotating, their velocity or speed is in this negative clockwise direction. So the negative sign, once again, is just about direction, but now it's direction of rotation as opposed to down versus up. Okay, so we've seen angular velocity as well as angular displacement. What do we have left? Well, first we can get to our instantaneous angular velocity, which is where we look at the limit of shrinking that time interval down to 0, and then we'd have our angular velocity at one particular instant, which no longer needs that average bar on top of it. In calculus, this would be known as a derivative, which is not required for this class, but we can just note that we can get the instantaneous angular velocity, which is the angular velocity at one particular moment in time, which helps us out. Now that we've defined that, let's get back to that question of what is left to discuss for our angular variables. Well, there will be cases where we have a changing angular velocity. If we have a changing angular velocity, we must have an angular acceleration present. So the definition of average angular acceleration is the change in angular velocity over time. Same as our typical acceleration, right? Change in velocity divided by time. For angular acceleration, we have a slightly different variable. We use alpha, a lowercase alpha, which is the Greek letter for a. So that part makes sense. But the way it's written is like this little fishy. So it's a sort of a stretched out A. If you imagine, instead of having an A with a vertical bar, it's like you grabbed those two little flaps and pulled them to stretch it out into more of a fishy shape. That's our Greek letter alpha. It's equal to the change in angular velocity, delta omega, divided by the change in time. And the SI unit will just be the SI unit of angular velocity divided by time, which comes out to radians per second squared. So this is very similar to our linear acceleration. The only difference is linear acceleration is meters per second squared. Here it's radians per second squared because we're looking at how the angle changes. It's the angular version of this. Let's look at this in an example as well so we can see it in action. So example 4, a jet revving its engines. As seen from the front of the engine, the fan blades are rotating with an angular velocity of negative 110 radians per second. As the plane takes off, the angular velocity of the blades reaches negative 330 radians per second in a time of 14 seconds. Find the angular acceleration, assuming it to be constant, which could also be find the average angular acceleration, but we'll often deal with a constant angular acceleration. So if we want to find the angular acceleration, we'll just take the final angular velocity minus the initial. Now, why are these angular velocities negative? Well, we can see that if we imagine ourselves looking at the front of the jet engine, which I don't recommend standing in front of a jet engine, but we can have a thought experiment, right, where we imagine this, and we'd see that they are rotating in the clockwise direction. That's defined to be negative, just by convention. So it starts out at negative 110, and it becomes negative 330, so it's going with a larger speed in that same clockwise direction. Let's plug this in. So if we then plug in our final negative 330 minus our initial negative 110, we would end up adding 110, dividing that sum by 14 seconds, and we'd come out with an average angular acceleration of negative 16 radians per second squared. Once again, this is negative, and that just tells you that the acceleration is acting in the negative or counterclockwise direction as well. So since the initial angular velocity was in the clockwise direction, having an acceleration in the clockwise direction means that the speed is increasing, which we did observe here. So that matches out. That is very comforting. What we'll get to do in the next section is put it all together into our classic kinematic equation. So stick around.